nice states, hello, I'm trying to memorize that gas laws and all of that, all things like that, Boyle's law and all of that, an easier way to memorize them. I actually don't have let's say like an easier way to memorize them besides the fact of looking at which ones like which ones measure what, meaning like Boyle's law we know measures, it only compares pressure and volume. And then that's where you know, okay, P1 V1 equals P2 V2 for Boyle's law. And then for something like, let's say, Charles' law, where that only compares volume and temperature, and then you know, okay, well, volume and temperature, this is going to be our other formula. So what I would recommend doing is writing them all down and then making sure that you know like which two which two things are they comparing really. Like let's say for Boyle's law we know it's comparing pressure and volume, and you know as one increases so does the other. And that's always going to be proportional to each other, so those will never be divided. That's one trick that you can see, that Boyle's law won't be the one that's dividing anything really. It's just going to be everything else, meaning like Charles' law with volume and temperature, because as one increases, the other decreases. That's known as inversely proportional. And then you can think of something like Avogadro's law. So if we have moles versus temperature and so on. And then the main one I'd say to definitely know, that's the most important to know, is PV equals nRT. That's the ideal gas law, nRT. So what I recommend doing is just writing them out over and over again. And like I said, see which ones, like what they're comparing for every single type and so on. So that's, I would say, the easiest way to memorize it. I don't necessarily have like a trick per se. That would be my trick, is just writing them all down and seeing what each one has. So that being said, let's keep going. Let me see what other question I got. So Alexandria says, could you review how to write the two half-cell reactions showing two elements becoming monoatomic ions? Example of lithium and nitrogen gas. Okay. Example of lithium and nitrogen gas. So them becoming, let me see that question again. All right, two half reactions, two elements becoming monoatomic ions. So you're stating if you have like lithium, that's typically in its solid state, plus nitrogen gas, that's going to be diatomic, so N2, and it's in its gas state. And then how that would combine, lithium nitride, but that's still kind of strange to leave it that way. How to write the two half cell reactions showing two elements becoming monoatomic ions. Let me see if I can show you that. One sec. All right. Okay, becoming monoatomic ions. Sure. I mean, what I would do here, by the way, like how I knew that lithium was solid and that N2 is or what it even was N2, was just the fact that lithium is a type of metal. It's in our first group. And then remember, those are alkali metals. Those exist in solid form when they're by themselves. So that's why I instantly knew that lithium would be a solid. And then nitrogen gas, the fact that it tells me it's a gas, that's one thing to relate. And the next thing is also just looking at it as it will be N2 since it's a diatomic atom, meaning it exists in pairs. Now, the next thing is this is going to form something known as lithium nitride. So lithium and nitrogen will then combine, and then we have to balance out our charges. So remember that lithium has a +1 charge, and then while nitrogen has a 3- charge, so we have to balance that out. Really, we're gonna pretty much move that 3 down, and that's what that would look like if we balance this out. And then lastly, we do have to balance out this overall equation, and then I'll show you oxidation numbers and just different half reactions of this. So real quick, this is what our overall equation would look like, and then we'll balance this out. So I'll start with lithium, and we see that lithium has 3 on the product side, so we need to put a 3 on the reactant side. And then nitrogen has a 2 on the reactant side, so we need, well, 2 more on the product side.
And then that changes, this really distributes, and it changes the amount of lithium, so to 6 because 2 times 3. So I'm going to go back to the reactant side and erase that 3 and change it to a 6. And as that loads, there we go. Okay, so now we're balanced. Now we're going to look at oxidation numbers. So oxidation numbers, there's one specifically, there's several to know, but the first one is that anything that only has one element and is in its solid state will have an oxidation number of 0. So then in this case, lithium's oxidation number is 0. Now the next thing is anything that is diatomic, so exist in pairs like N2, H2, O2, and so on, those will also have an oxidation number of 0. So this is also 0. Okay, next thing to note, now that we have a compound, anything that is in group 1, so the alkali metals, will have an oxidation number of +1. So in this case, lithium would have a +1. Now we want to figure out what is the oxidation number of nitrogen. So then in this case, I'm going to multiply 3 lithiums times the oxidation number of 1. So it really gives me 3. And then I need to make this a neutral compound, meaning it's going to add up to 0 because there is no charge for this compound. And then that would give me, here, I'll show you. So I'm going to put an X just because we don't know it just yet. And then we'll solve for X and I'll subtract over the 3. So really the oxidation number of nitrogen would be -3. Okay, so this is what I'm looking at, by the way, when I'm looking at oxidation numbers. This 3 just helped me figure out what the oxidation number of nitrogen was. Now that we have that down, let's look at how our electrons are being moved, if they're either gained or lost, and so on. So how I think of oxidation or reduction, well, with oxidation, I'm looking at what's becoming more positive. And then with reduction, I'm looking at what's becoming more negative. So with oxidation, which one's becoming more positive? Well, lithium, because it's increasing in its positive charge or oxidation number, really. And so this is going to be oxidation. And then next, which one is being reduced or becoming more negative? Well, that would be the nitrogen. This is going to be reduction. And then now, if I'm looking at this, and just to kind of let you know how I knew which one was being oxidized or what's undergoing oxidation, as I said, it's going to be going from the reactants to the products and looking at which one's becoming more positive. It's becoming more positive because it is losing electrons. So think of it this way: if you lose negative people in your life or negativity, you become more positive. And then now vice versa with reduction, you are gaining electrons because you are gaining negativity in your life, right? You're becoming more negative. So that's how I want you to kind of think of it. Okay, so now going into our half reactions. So with oxidation, I'm just going to look at what is undergoing oxidation so I know it's that lithium. So I'm going to keep this balanced and put that this is 6 lithium solid. And then I'll say 2 Li lithium nitride. And then I'll also state the other half reaction, so the reduction portion of this, N2 in its gas state, and then this would be 2 lithium and then nitride. So that's not changing. Now, the next thing that I want you to focus on are how many electrons are being gained or lost. So I'm going to go back to this equation and look at this and see, okay, I want to look at the products, how many electrons there were in the products minus the reactants. So for lithium, we have 1 on our product side minus that 0. So only 1 electron was lost in this case. And then now looking at reduction, where we started with a -3 and we're going to 0, that would then give us -3 or just 3 because we gained electrons. And that's why it's really, you're thinking of it as negative. I wouldn't say to focus too much on that negative. It's just to see how many, like what our number is. So that's telling us how many electrons were gained. So 3 electrons. And that's what I have to add to these half reactions. So then for oxidation, you will always add the electrons on the product side. For reduction, add them on the reactant side. So reduction, reactants. Okay, that's how I want you to remember it. So for oxidation, I'm going to add just 1 electron since that's how much was lost. And then for reduction, I'll add 3 electrons since that's how many electrons were gained. So that's what I would say to do. That's how we approach these half cell reactions. Hope that helped. I'm going to move on to the next question. And let's keep going. Okay. So next question, can you define precipitation reaction? Sure. So a precipitation reaction is going to form something known as a precipitate. That's a fancy word for a solid. Okay. So that's all I really want you to think of is that a precipitation reaction in the product side, there will form a solid. So that's how you know it forms a precipitate. And I'll show you an example with that real quick. Let me find all of my little examples with different types of reactions. But that's the easiest way I'd say to look at it is that's going to be the main thing to even tell all of these reactions apart. Whatever forms a solid will then be a precipitation reaction. And I have an example right here. So let's say if we had a nickel nitrate and it's in its aqueous form, and then I'm going to add that to, and by the way, this is already balanced. I'll add this to, I forgot the B, KBr. There we go. And it's in its aqueous form. And then we also have 3 potassium NO3 in its aqueous form. And lastly, nickel Br3 in its solid form. So right there, you see, okay, well, we started off as everything being aqueous. And then we ended up with something being a solid. That's what a precipitation reaction is. That's what a precipitate is. So the main thing that you might want to also look at, and you might have been told this already, was understanding how a solubility table works. So what a solubility table does is it tells you how can these two, like when we put these two elements together and form that compound, will they be soluble or insoluble? Cool. So awesome. So that defined it, but that's what I want you to think of. Solubility tables, you might see that very soon. I'm going to move on to the next question. And let's see what else we got. So Courtney states, significant figures, I need more help with knowing when it's a leading zero and when to use them or not. Okay, so you're asking significant figures, I need more help with knowing when it's leading zeros. I can give you different examples. So let's say if we have 0.000500, sure. So something like this. Our leading zeros were kind of what they're stated already. Like they're the ones that are leading. They're the ones that are in front. So in the very beginning. So these ones. And then these we're going to state are not significant. They're not sig figs whatsoever. But everything following that, once we have a number that is not zero, and like 5 in this case, then we can continue counting anything that is after that non-zero number would be significant. So in this case, we would have 3 sig figs just because of this 5. This 5 is telling us, all right, we're going to start here. And now we have 1 sig fig with 5, and these remaining zeros after that 5 would be significant. So in this case, there would be 3 sig figs or significant figures. And then I'll keep doing a couple more. So let's say if we were to have, I'm going to kind of mix them up, 0.4802 or 0.008, I'm going to say 10, sure. Okay, so if we're doing something like this beginning zero would still be considered a leading zero, so nope, that doesn't count. But then everything thereafter, once we start to see that non-zero number, that's where I want you to think, all right, this is where the sig figs are starting. So then right here, this is where all of our sig figs are starting. So we have 1, 2, 3, and 4 sig figs in this case. And then we'll continue with the next one and see, well, no, that's not significant. That's not significant. Neither that. Now that we finally got to our non-zero number, which is that 8, then we know our sig figs are starting. So, okay, 1, 2, and 3, that would be 3 sig figs. Hope that makes some more sense. And then you also mentioned and when to use them or not. So you will always be using significant figures, at least in your first class of chemistry, just to kind of let you guys know. Later on, depending on your professor, you will not use them. They're actually really not relevant. I know. But in the beginning, you will always use them. Like I said, it does depend on your teacher. But I would say definitely know all of those sig fig rules just in case. So like, let's say if you were doing real quick, another question that you had 3.05 times 0.004, and you were told to calculate this. So this is kind of something that I would say you definitely need to know your sig figs from, and just seeing like this first one would be 3 sig figs for sure, since anything that's sandwiched in between two different non-zero numbers would be significant. These are not significant since they're leading zeros, and we'd only have 1 sig fig. And then whenever we're multiplying, remember that you have to look for the least amount of sig figs. So after you do this multiplication, you would only round to 1 sig fig. So that's what I want you to kind of think of. You will be using these typically. Okay, cool. I'm going to move on to the next question. Okay, hey, can you go over wavelength and frequency? Sure. So with wavelength and frequency, and really just the spectromagnetic spectrum, there are several different formulas that you want to look at. So what I'm looking for right now real quick is just for some examples to tell you guys that here. I think it's in my second one. Yeah, it is. All right, here it is. So the main equations that you for sure got to know, all right? The main one is going to be E is energy is equal to Planck's constant, so H, times the speed of light, c, divided by our wavelength. So that's one to definitely know. The second one is going to be no energy is equal to Planck's constant times velocity, or sorry, frequency. V would be our frequency. And then the last one, frequency is equal to c over wavelength. And by the way, the reason why I said velocity for that, it's not even a V. Later on, you'll get to that, and that's actually a little bit of physics too. But what I want you to focus on, that kind of V-looking shape, is just our frequency. So those are for sure ones to know. Let's go ahead and do like an example just to show you how to use everything and what all of your constants are. So let's say if we're trying to find frequency, and we're given that, okay, we have some sort of wavelength, and this gamma-looking shape is just wavelength. And let's say we have 589 nanometers, and we're asked to find our frequency. So first things first, it's just figuring out which formula should you use. So what I want you to think of is, first off, I need to have both frequency and wavelength in my formula. So that's the one I have to use. So then, okay, which one has both wavelength and frequency? Well, the third one. So that for sure is the equation that I'm going to be using. And something to note, c, or the speed of light, is known as 3.0 times 10 to the 8th meters per second. By the way, you might have also seen it like this, 2.998 times 10 to the 8th. Each one is correct. It just depends on your instructor. Okay, so now the main thing for this is you always want your units for wavelength in meters when you're plugging into these formulas, because our speed of light is in meters. So that's why we have to have it still be consistent and have that cancel out. So I'm going to plug that in. So actually, sorry, before I plug that in, let me go ahead and change my nanometers to meters. So step 1, change your nanometers to meters. So looking at this, we have 589 nanometers times, now we're going to go ahead and do a little bit of unit conversions where our nanometers would go across from each other. And I'm always going to put 1 nanometer to 10 to the negative 9th meters. And so when I do that, that then gives me 5.89 times 10 to the negative 7 meters. Okay, now that I've converted meters, now you can plug in. So that I would say is where students get a little bit kind of like marked off points, or they get tricked, unfortunately, is just because you forget to change it to meters. So definitely do that first. Now I'm just plugging in my speed of light, or c, on top, and then divided by the wavelength, which I just changed its units. So, okay, now we'll go ahead and divide. But first, I want you to note that the meters and meters would cancel. That's awesome. That's what we wanted it to do. So we know we're on the right track. And then let's see what this would have been. I forgot I have these already done. So when you divide everything out, this would give us 5.0899 times 10 to the 14th. Seconds to the negative first. I would round to 3 sig figs in this case, since our initial question only provided us with 3 sig figs, 5, 8, 9. And then I'll round this, stopping right here, and I'll round up. So 5.09 times 10 to the 14th, seconds to the negative first. That would be our frequency. So that's the main thing that I want you to focus on when it comes to these types of questions, is which equation are you using, or which formula are you using? And the easiest way to see it is, what are they giving me? What am I finding? So because you had, in this case, you had frequency and you had wavelength, you know that your equation has to have both of those. Okay. So that's going to be the main thing to look at. Moving on. Let's see what else we have. Okay. So Brian asks, can you help explain naming ionic and covalent compounds? Sure. So when it comes to ionic and covalent compounds, and by the way, I'm going to see if I can put a video link to help you out even further. I have a whole video on naming ionic and covalent compounds that I do a bunch of examples on, so I'll definitely link that up. But for now, let's just go ahead and practice a couple of them. Okay, so with naming ionic and covalent compounds, the main thing you want to focus on is what type of compound it is initially. So that's going to be step 1. If it's ionic, remember that's going to consist of one metal that's going to be positively charged and one non-metal that will be negatively charged, and it has to be in this order. How I personally remember it is you want to be positive before you're negative. Okay, so that's going to be our ionic compound, and I'm going to start with just the different types of naming for ionic compounds overall. So we're always going to have the name of our metal first. It's always going to be the case when it comes to something being ionic. And then next, what will then follow would be the non-metal ending in "ide." All right, so it's going to end in IDE or "ide." So let's say if we had something like NaCl. Okay, so we know that Na is a type of metal, and then Cl is a type of halogen, which is also known as a non-metal. So in this case, we'll state the name of the metal, or Na, which is sodium. And then we know our non-metal would be, it's typically chlorine. However, we have to make it end with "ide." So instead of chlorine, it would be chloride. So that's exactly what we'll put here. So chloride. So you're really just going to remove, like instead of putting that this was chlorine, you're just going to remove this "ene" and then change it to "ide" for every single non-metal. Okay, so that's something to definitely note for something that's ionic. And then now let's do one more example with ionic equation or compounds. So let me go ahead and put something, let's do polyatomic ions. So for our polyatomic ions, that is when we have, let's say, NO3 with a minus charge. Those are going to be ones to for sure know and just memorize. So NO3 minus is known as nitrate. And then for, let's say if we're putting something like, let's say if we had something like this, and I'll show you what to do. And by the way, I'm going to put that link for you, Brian, because it's going to be so much easier. I have all of the steps perfectly laid out in that video, and even some practice problems for you. So here. So let's say if we have something like this, so Fe is known as iron. That's the name of the metal. And that's what I'll state here. Now, iron is a type of transition metal. So a lot of times, and I don't want to say for every single type of transition metal, but a lot of times for these transition metals or these metals that have multiple charges or multiple possibilities for charges, we have to place some sort of Roman numeral telling us what the charge was in that compound. So in this case, the charge of iron would be 3. And how I personally knew that was because nitrate, or NO3, has a -1 charge, and then this 3 subscript must have been placed there to balance out the charges. So that's like you're going backwards, and iron would then have a 3+ charge. So I'll place a 3 Roman numeral there, just stating that for sure that has to be there because iron's charge was 3. Your metals will always be positively charged. Now, I'll then state, instead of placing ide or anything like that, I'm putting that it's a nitrate. Real quick, ate and ite refer to something being polyatomic, meaning there's multiple atoms or multiple elements kind of placed together, okay? So poly meaning many, and then our atoms really just looking at there's multiple nitrogen and multiple oxygen together. And then ions, of course, just state that it's charged. So, and then however, when it's ide, that refers to it just being one element. All right, so that's the main thing that I want you to kind of focus on with those. Lastly, covalent compounds consist of 2 nonmetals. So for our covalent, it's just 2 nonmetals, and we're never going to balance out our charges for that. Instead, what I want you to look at is there's going to be different types of prefixes. So your prefixes, like let's say di meaning 2, tri meaning 3, tetra meaning 4, and so on. And like I said in that video, I go in through every one. Don't worry about that. So what I really want you to think of is for covalent compounds, they're pretty much telling us how to write it automatically. Like, let's say if we had something like tetra, let's say tetra phosphorus. I'm going to say dichloride. Sure. Okay. So tetraphosphorus. So tetra just refers to there being 4. We know what phosphorus, that's P. So that means that our subscript, that tetra, just tells us the subscript. And then now for chloride, or really chlorine, I'm going to put Cl. I know this di is also telling me the subscript, so that's 2. So that's going to be the main differences with ionic and covalent. Ionic, you're always going to balance out your charges and make sure that those are good and fine and the same. And then for covalent, you never balance the charges. That's why the prefix is there. So definitely check out the video. I'm going to move on to Norma's question. Okay. Let's see what we got. Can you please explain Emil's conversion problem? A toothpaste contains, and let's see, thank you for putting the question, by the way, 0.252% by mass of sodium fluoride, NaF, it's an N, okay, NaF, and then used to prevent dental caries, and 5.6% by mass of potassium nitrate. Which decreases pain sensitivity. One tube contains 109 grams of toothpaste. Okay, so I'll say this is just toothpaste, and this equals toothpaste. I spelled that so wrong. And this equals one tube. Okay, let me see what I'm asked to find. Contains that. What am I asked to find? So, Norma, for this question, is it asking to find? What is it asking? Sorry, there was no final question with it. Oh, there we go. Okay, got it. How many formula units? Okay, yeah. How many formula units are in the tube of toothpaste? How many grams? Okay. All right. So let's start off with the first question. Here. Oh, I'm running out of room. Okay. So how many formula units are in KNO3? And I'll get to the second question. Okay, so let's just start off with how much we know there already is. So we know that we have 119 grams of, I'm going to say toothpaste. Okay, and then now what they're providing us with is a percent by mass, and that's going to be used as a conversion factor to allow us to get to something a little bit different. Meaning, right now we just have the toothpaste, but we need the actual compound. So that percentage is going to allow us to get there. So this is what I'll say we'll do. And you know what? Let me go ahead and change this. This is okay. That's better. I needed more room. One sec as I finish this. Come on. Okay. So pretty much what we're going to be as this decides to load. Sorry about that, guys. There we go. That's better. Okay. Once again, I'll start off with that 119 grams of toothpaste. And then what I want you to focus on is that percent by mass, specifically of KNO3 or potassium nitrate. So they're giving us that it's 5.6% by mass, okay? What this really refers to, since it's a percentage, it's going to be out of 100 grams, okay? So what I'm going to do is I'm going to put that 5.6 on top, and that's really the grams of our actual compound or potassium nitrate. And then 100 grams is of the entire tube or the toothpaste in general. So that's really what is hidden within that percentage. Is you're allowed to do that, by the way, is just place this under 100, since that's what a percentage is. It's out of 100. So this is what we're going to use to allow us to get to grams of KNO3 and then work our way to formula units. So that's what I'll do here. So I'm going to align those units across from each other. So placing that 100 grams of toothpaste on the bottom, and then 5.6 grams of KNO3 on top. And I'm going to keep going. So now that we've gotten to grams of KNO3, we need to somehow, some way get to formula units. So remember that there is no bridge or conversion factor that perfectly allows us to get to formula units, like automatically from grams to formula units. We have to convert to moles. So our next step is going to go to moles of KNO3. And then lastly, then we're going to use Avogadro's number to get to formula units of KNO3. Okay. So that's what I'll do here. I'll place grams of KNO3. And what I'm using for this, by the way, is the molar mass. So this is for every 1 mole. So let's calculate the molar mass of KNO3. Molar mass is just the individual sum of each element's mass, really. And I'll show you that here. So looking at the periodic table, our potassium has a mass of 39.10. Nitrogen has, I believe, 14.01, and oxygen has 16. However, there are 3 of them, so I have to multiply that by 3. 16 times 3 gives me 48, and I'll add all of these numbers together. And that would be the overall molar mass of this compound. So let's see what we got. Okay. So we'll have 101.11 grams per mole, and this is of KNO3. All right, so let's go back to our little table here. And so we said it was 101.11. That would be on the bottom. That's our molar mass. And what you're going to see me do each time is all of these units across from each other will cancel. So, okay, those are canceling. Now we're at moles. We're at this step. So we can finally use Avogadro's number and change this to formula units. So changing this to formula units, I'm going to place the moles and moles across from each other so they can cancel, and Avogadro's number will go on top since we're solving for formula units, so that's why it has to be on top. All right, and I'm going to say formula units. So let's see, KNO3, there we go. Okay, so formula units, we're finally there. I know these questions tend to be long, so I'm just going to multiply straight across and then divide by 100 times 101.11. All right, so let's see what this gives us after we multiply everything out. And then we'll check our sig fig count just to double check we have the proper ones. And what do I get? Okay. So I get 3.9690 times 10 to the 22nd, and this would be formula units of potassium nitrate. And let's make sure we're rounding to the correct amount of sig figs. So I would look at what we were given initially. So the two significant figures for that conversion factor, I would look at that and see I'm just going to round here. So I would round up. I would round this up to 4.0 times 10 to the 22nd formula units of KNO3. So that would be for that. And then let's see if I can get to any more of those questions here. So that would be at least be the first one. But for the next one, I'll show you how to set it up. How many grams of sodium ion are in 1.20 grams of toothpaste? So we'll start off with that 1.20 grams of toothpaste. And then we're going to make our way again. This is now saying of sodium. So the same sort of concept here is what you're going to do. Now with that second percent by mass, once again, I'm going to put this over 100 grams of toothpaste, and that's what I'm going to use as my conversion factor. And this would be the grams of Na, this was sodium fluoride. And then, so this is what I'm going to put here. So 100 grams and so on of toothpaste. And then placing that 0.252 grams of Na fluoride. And then this question, these cancel and these cancel. This question is asking for how many grams of just the sodium ion. Well, if we're looking at that, you would need some sort of, and actually it's just asking for the ion. It would just mean that it's a 1-to-1 relationship, meaning it's 1 mole. So before I get ahead of myself, let's just look at the molar mass of NaF. So real quick, Na is 23 and fluorine has a mass of 19. And then we'll add those together and we'll get 42. So that would be on the bottom. This is for every 1 mole of NaF. And then we're trying to get to something completely different. So we're trying to get to moles of just the sodium ion. And since there's only 1 sodium in this case, I can state that there's only 1 mole of Na. And then, by the way, if this were like HO2 and then H2, I'm sorry. If we had something like that, you would state, like, let's say if we're looking for hydrogen, you would look at the subscript on the bottom and see that there's only 2. So since there are 2, there would be 2 moles of H for every 1 mole of H2O. But however, in this case, Na, there's only 1. So that's why I'm able to do that. And since it's stating the ion, it's really just referring to the element itself, or ion, it being positively charged. But we'll get there. So, and then the last thing, how many grams? So last step here, 1 mole on the bottom, I just need the molar mass of Na. So that would be 23 Na. And then that's what I want you to multiply out. So it would be 1.20 times 0.252 times 23 divided by 100 times 42. So that's what I want you to kind of do with these types of questions. And then the same sort of concept for fluorine. So instead, what you would do, instead of going to moles of Na, you would just go to moles of fluorine since there's only 1. Same thing here, only 1. And then I'll just put the moles of, or the molar mass of fluorine on top. So just 19 on top. And that's what you would multiply out. So that's what I'd want you to do. By the way, all of these numbers would be the same. It's just the 19 grams, that would be different. So, and then if that's asking for mass, how many fluorine ions are in the tube, you might have to do one extra step actually. So then you'd go to, if it's asking for grams, I think it's actually asking for many fluorine ions. I would think atoms. For fluorine instead, I'm sorry, since it didn't say mass, I don't know, I thought it would be the same one, but they're doing atoms instead. Do Avogadro's number on top. And really, since they're asking for fluorine ions, I'm assuming they're asking for the atoms or some sort of particles or something like that. But you would do Avogadro's number on top for fluorine ions, essentially. Okay, so that's that whole question. I'm going to move on. Let's see, can you go over limiting reagents and excess reagent problems? Sure. All right, let's see how I'm doing. Okay. And I actually just did a video on that as well of limiting reactants or limiting reagents. So definitely check that out. It's my latest video. Just to kind of also let you guys know as I searched for one of these questions. For these types of questions, I also did I made my own notes. So what these notes entail or what they are, it's pretty much like a guide to figuring out limiting reactants. I show all of the steps. It's ridiculously detailed. So I show you how to figure out, limiting reactants, excess reactants, theoretical yield, percent yield, actual yield, all of that. And it's really detailed. So I definitely recommend doing that. I also just released another one on molarity. So that's how to figure out how to find molarity, how to even use molarity as a conversion factor for like solution stoichiometry or titration questions. And I even put dilution questions and serial dilution questions in the molarity notes. So I just put the link in the chat. Definitely check those out. They're ridiculously helpful. I make sure to make it very detailed. And I even put really common test exam like questions on there. And I even put other ways that they can word it on your test. So yeah, definitely check that out. Okay, so for limiting reactants are always going to be the reactants that run out the fastest and they produce the least amount of product. So now let's see what we got for this first one. Let's say if we have N2 plus 3H2 going to 2NH3. And we were given initially that there's 14.32 grams of N2 and that we have 4.21 grams of H2. So they're just giving us our reactants, how much mass of our reactants we have of each. And then they're asking us what's the limiting reactant. Okay. So for limiting reactants, your step will always be this. You're going to go from grams of your reactant to grams of your product, which in this case is NH3. And we have to do this for each reactant, okay? So let's say if you started off, if instead this was moles that they provided, then you'd go from moles of reactant to grams of product, okay? So that's what I would state to do every single time. Now, let's go ahead and do this. So I'm going to build a plan going from grams of N2, and I'm trying to make my way to grams of my product NH3. So first things first, you don't know where to start, change it to moles. So changing to moles of N2. Now that we have to change the compound, we have to use a mole to mole ratio, which comes from the balanced equation. So moles of NH3 is where we want to get to next, since we're trying to figure out or get to grams of NH3. And then lastly, we'll go to grams of NH3, which comes from using the molar mass. So this first step is going to use the molar mass of N2. The next step, mole to mole, will just be a mole to mole ratio. And then lastly, this last step would be moles to grams, which is just using the molar mass, but however, it's of NH3 this time. So let's set this up. So I'm going to start with the given. They start off giving me 14.32 grams of N2. And then I'll make my way to grams of NH3 using this little plan that I showed you before. So placing the grams of N2 and 1 mole of N2. Now, this is going to be the molar mass of N2. So N is really 14.01. I'm going to multiply that by 2. So we'll get 28.02. There's a decimal there. And then I'm going to keep going. The grams and grams would cancel. Now we're at moles of N2. And I want to do a mole to mole ratio to get to a totally different compound. I'm going to go back to my balanced equation. So looking at my balanced equation, if there is no number or coefficient in front of that compound, assume it's just 1. So now we have 1 mole of N2 per every 2 moles of NH3. And that's what I'll place here. So 1 mole for every 2 moles of NH3, and we'll keep going. So last step with this one, I'm going to grams of NH3. So moles of NH3 on the bottom per every gram of NH3. Let's figure out the molar mass of that. So N we said was 14.01. Hydrogen is 1.01 times 3 since there's 3 of them. So it would be 3.03. Add these two up and we'll get 17.04 grams of NH3 per every 1 mole. Okay, so now that everything has canceled out and we finally got to grams of our product, we'll multiply and then we still have to keep going. Okay, so if we multiply that out, we'll get 17.43 grams roughly of NH3. And then from here, I'm going to check. So that was just N2, by the way. That was seeing what that reactant would be, or of N2. So now I have to check the other reactant. So H2 is the next one I want to check for. And I'll start off with the 4.21 grams that they gave us initially. And I'm going to make my same exact thing here, where I'm going from grams of H2 to moles of H2. And then next, moles of our NH3 to then grams of NH3. So same exact sort of setup. I'll place that this is roughly 2.02 grams of H2. And then on top, this would be 1 mole of H2. This is just that molar mass of H2. And then keep going. This would be a mole to mole ratio going to moles of NH3. And then next, let's go back to our equation and look at our balanced equation to figure out how many moles, what's our mole to mole ratio really. So there are 3 moles of H2 per every 2 moles of NH3. So 2 on top, 3 on the bottom. And we'll keep going. So our grams and grams of H2 would cancel. Moles and moles of H2 would cancel. And then now we have to use, once again, the molar mass of NH3, which was 17.04 grams per 1 mole. And then let's see what that gives us. And then we'll compare those values. So this is 23.68 grams of NH3. And then really, and actually this should have been a 2. That should have been a 2. Just little side note. Okay, so we would compare how much of each reactant. We would compare each reactant and see how much does each one make in product of NH3. Okay, so then 17.42 grams of NH3 would go for N2. That's how much that reactant produces. And then 23.68 grams of NH3 is how much our H2 produces. So whatever product is the least amount of grams, then that would be your limiting reactant. So N2 would be our limiting reactant. Now for H2, that means it's then our excess reactant. So that's the main thing that I want you to look at. You're always going to go from grams of reactant to grams of your product. Unless of just one product, unless they start off with moles of reactant. Okay, then you would just go moles of reactant to then grams of your product. And then you figure out which reactant produces the least amount of product that is your limiting. And the one that's left over is then your excess. All right, so that's what I want you to focus on. Let's see if I can answer another question. What else do I got? Okay, let's see. Can you go over quantum numbers? Yes. So let's go over quantum numbers real quick. So with quantum numbers, this is really going to talk about more orbitals, okay? So, and this also has to tie into electron configuration. Let me see. Here they are. All right, I have some examples for you. So there's 4 different types of quantum numbers, and I'll jump to that now. So the first one is known as N, or it's also referred to as our principal. So this is going to tell us the size, or really how strong in energy that orbital is, okay? So your N could be anything like 1, 2, 3, and so on. Really what we're focused on our periodic table, and if you already moved past electron configuration, which you should have if you're on quantum numbers, then that's going to talk about the row that the element is in. So like let's say our first row, that would be 1. So then N is equal to 1 here, because that's our first row. And then 2, okay, well, N is then equal to 2 here, and so on. So that's what we're focused on. We're seeing how large that orbital is, what's the size, what's the energy level. Okay, and I'll keep going, just explaining each one, and then I'll give you an example. The next one is going to be referred to as L, or its angular momentum. This is going to define the shape of your orbital. So whether it's S, P, D, or F. There's a specific table to know, okay? So if L is equal to 0, then that means it's an S orbital. If L is equal to 1, then it's P. If L is equal to 2, it's D. And lastly, if L is equal to 3, it's F. All right, so I'd say for sure know that. The reason why this is because it's 0, since S is the lowest in energy and F is the largest. That's why it has the largest L. That's kind of one way to look at it. Another one that we'll see that correlates with L is something known as our magnetic quantum number, where it's shown as M sub L, meaning that's going to talk about the orientation of our orbital, whether it's, think of it kind of like whether it's looks like this is like a p orbital, whether it's py, px, pz. Don't worry too much about that. The main thing that you have to focus on is just the fact that M sub L is going to equal your negative L to positive L. What this means is, let's say if we found that our L was 2, okay, then M sub L has to be between -2 to +2. So then I'll place all the numbers in between. So this has the possibility of being -2, -1, 0, 1, and 2. And that would be the same thing now if like we had L is equal to 3, then we'd include M sub L would be -3, -2, -1, 0, 1, 2, and 3. So that's what I want you to kind of look at. And lastly, the last one will denote the spin. So our spin is M sub S, where this is just talking about the spin of your electron. So let's say if we were to kind of look at the different spins of our electrons, something like that, this is going in the positive 1/2 and negative 1/2. That's why you typically see this as plus or minus 1/2. So that doesn't really change. Now, if you were given something like let's say if they gave you, find the quantum numbers of 3p. So if they had something that was a 3p orbital, or even if they just said the electron configuration ended in 3p6 or something like that, really I'm just going to focus on 3p, then this automatically tells you your quantum numbers. Okay, so I'm just going to look at 3p for right now. And this 3 tells us what the n is, right? So then n is equal to 3. That tells me really the row on our periodic table. And then that p, that goes back to whatever L was. So going back to this little table that we made, well, p refers to L equaling 1. So, okay, well, then L is equal to 1 in this case. And then remember that M sub L goes hand in hand with whatever L was. So that was negative L to positive L. So then this has to be -1, 0 to +1. That would be our M sub L. And then we'll have the possibility of our spin M sub S to be plus or minus 1/2. So that's going to be like the easiest way to kind of look at this. Now that you know what each one refers to, that N is really that number in front, and then P, D, F, S, any of those types of orbitals refer to whatever L is, and so on. And M sub L tells us really just refers to whatever our L was, both negative and positive. Okay, so that's what I want you to kind of look at with this. Okay, so we're a little bit out of time. So sorry, guys, for the technical difficulties this time around. But I actually have to go to tutor more students afterwards. Now, I did want to kind of let you guys know I will be releasing another video this week, and it will be on molarity. So if you guys are, struggling with molarity, that will be up. If you need more immediate help with molarity titration questions, using molarity as a conversion factor or dilution, serial dilutions, I have notes that I created that are ridiculously detailed and just amazing. Personally, I worked very hard on them for you guys, so definitely check those out. And make sure to sign up for any pretty much just, I want you to join this beautiful community that we have here. I'll go ahead and place the form It's going to be in the description box actually right after this video, right after we stop going live. So I'd say definitely check it out. Join the community. My gift to you is a formula sheet that you will receive, and it is all the formulas that you will possibly need to know and see this entire semester or school year overall with chemistry. So definitely check that out. It will be in the description box after this live session. It is also in every single one of my videos description boxes. So if you haven't already done so, join the community. And then I'll be seeing you guys also next Sunday, and we will be at 12 o'clock, making sure that the audio and everything is fine. But yeah, thank you so much for joining me today, and I'll see you guys next Sunday, I guess. So have an awesome week. For those of you having exams, do your best. Keep working hard. You got this. All right. I'll see you guys next Sunday.